theoretical model for how these planets would stay in their orbits. So they would introduce concentric spheres. They would introduce they actually really thought about them as being physically attached to other physical objects. Of course, these spheres had to be transparent, otherwise we wouldn't be able to see things beyond them. And so there were Earth wasn't a planet. There was the sun, and then there was the moon, and then there were 6 planets altogether. Sorry, 5. That Earth would be the 6th one. So the universe, and then there was the sphere of fixed stars. The stars were all the same distance attached to yet another sphere. That sphere didn't move, or rather, in the ancient view, that sphere had to rotate around the Earth every 24 hours because Earth didn't move, so the rest of the universe had to move around the Earth. The view has become quite a bit more complex, but in some ways they're also quite a bit more simple. We actually understand how things happen now. So Greeks had to kind of introduce things without explaining how that happened. The universe now, the way we understand it, is about 14 billion years old. It has started from a very small and very dense and very hot state we call Big Bang, and has been expanding ever since, and as you will find out, will continue to expand. And so really we have come a long way, although there were ups and downs, as I will discuss as well. So if I want to measure distances in the universe, ideally I want to use geometry. Geometry, there are no assumptions. If I can measure angles of a triangle, if I can measure one side of the triangle and 2 angles, I can solve the triangle. And then I don't have to assume anything else. This is ideally, that's what I will be doing. This is how we measure distances on Earth. This is called triangulation. If I have a base and I have a way to measure distances very well, I will be able to measure precise distance. So we'll start with measuring the size of the Earth. Once we have the Earth as the base of our measurement, we can then measure distances in the solar system. We can measure how far away planets are from each other and from the sun. Once we have that, we can use this as a base and now measure distances to stars. Again, remember, you're way back. You have no idea how far away things are, so you have to kind of plan for measuring this. You have sizes of the stars. Then it turns out the stars we are part of a thing called Milky Way. It's a galaxy, as we call them now. So we would like to understand how big that object is. And then also we'll be measuring distance to other nearby galaxies. And eventually we'll put it all together and we'll want to measure the size of the universe, of the whole entity that we are in. And this procedure is commonly known as cosmological distance ladder. We build these steps one after another. Of course, in science, in reality, it's never that simple. As we change on one step, we'll make modification to the other steps, and we'll eventually know how big the universe is, how far away objects are. And so on your left, that's the plan. We start from Earth and we go all the way to heaven, to the farthest reaches of the universe. The ladder is sturdy, it will support you, and you can do your work. When I was a postdoc at CFA in Massachusetts, when you apply for one of these Hubble fellowships, you actually have to say what they're going to do. They don't just give you money to say, well, go wander the streets, do whatever you want. So you actually have to propose. So my proposal was that in fact, turns out that this distance ladder, some of the farther ranks, they're well measured, but some of the closest ranks, namely how far away the nearby galaxies are, was surprisingly poorly known back then and even still now. And so I had this idea in mind that I should find some really broken ladder to show that, my work will be about really fixing these 2 lowest ranks. But this was when the internet was younger. You couldn't find everything on the internet like now. You actually, now some things didn't exist. But at some point my neighbors threw away an old ladder in their trash. So I took the ladder, took it home, I kind of put it together, you can see, with tape and string, and took a picture. The problem is, now I have to throw away the ladder again because I don't want to keep it, but it's kind of awkward when you put a ladder from the neighbor's trash into your trash, so I kind of had to hide it. Anyway, so this was for a while when I would give a job talks, I would say, well, this is what I'm trying to do, is fix these lower ranks of the distance ladder. Again, so geometry. If I know the base, let's say I measured with a tape, or whatever method you use, of a triangle, and I can measure these 2 angles, then it's just from simple geometry, I can solve the whole triangle, so I know the sides of the triangles. This is a simple idea. The problem is, in astronomy, I will know this base. Let's say this is the diameter of the Earth, but then objects in astronomy usually are very, very far away, so both of these angles will be close to 90 degrees, and this angle will be very close to 0, namely it will be a very tiny angle. So the crucial thing in astronomy historically is my ability, how well I can measure separation of two objects, two stars, or a planet from a star. And the more precisely I can do it, the better I'll be able to measure distances. This is still something we want to do better and better. Even in the 21st century, our ability to measure angles has been improving, but we still want to improve it. The better I can do it, the farther away I can go and measure distances in the universe. So triangulation, of course, is well known on Earth. This is how people know how big, a country is. They actually would go and set up these triangles. This is from 19th century in Germany, and they would, measure all the angles and all the sides, and this way you actually knew how big your country is. This is surprisingly late in the game. They really was properly done in Europe only in 19th century. They would draw maps, but they were kind of not actually very accurate until they have done these experiments. You can make, two sides of your this could be a mountain, this could be a mountain, this could be some remote mountain. If you can measure these angles very well, you actually know how big things are. So let's start with the size of the Earth. The idea is again simple. Here, the base of the triangle is two different places in Egypt, which at the time was actually part of the Ptolemaic Egypt. So Ptolemy was one of the generals of Alexander the Great. Once Alexander the Great died, probably with some help, the generals divided the empire into the various pieces, and Ptolemy was one of the he was Cleopatra was one of his. He was ancestor of Cleopatra down the line. I think she was the last of the line. Aristotle's at the time Alexandria became established, really the center of the knowledge kind of shifted from Athens to actually Alexandria. Alexandria established the library, famous library, and Eratosthenes of Cyrene was actually the second librarian, the main librarian of the Alexandria. And he came up with this very simple idea. Basically, he was told, he never actually did the experiment, that at a certain place in southern Egypt, there was a time of the year when the sun was directly above the head. So this gives you one angle. And at the same time, he knew that the sun is about, I believe, 7.5 degrees away from zenith in Alexandria. So now you have the base. He also knew how far away these two cities were. So you have the base, you have measured the angle, one is 90 degrees, one is 90 degrees minus 7 degrees. You can actually now solve for an equation for how long the circumference of the Earth is. And so his estimate comes to about 46,000 kilometers. The actual number, it is about 40,000. So this is actually very, very precise, namely off by about 15%. In detail, this is actually, Eratosthenes wasn't an astronomer really, he was a geographer. This is the map of the world as he knew it. And notice obviously there is no America, neither northern nor southern. There's also no Australia. But nevertheless, he makes a measurement. It comes to pretty close value. These are the two cities in Egypt. Here's a Google map. Sorry, I skipped. There's supposed to be something showing up, but if you look closely, there is a systematic error. His measurement, what we call systematic error, is something you didn't think about when you try to make the measurement. Ideally, this measurement works when the two cities are on the same meridian, but they're slightly off. So that partially explains why he overestimated the size of the Earth. And then if you go for detail, there is a little detail that, of course, he used different units of distance because meters were not introduced until French Revolution. And so he translated his result into what we call stadia, length of the stadium. And so depending how exactly long the stadium was, this comes to a different number, but it's about 46,000 kilometers. So it's 15% too large, but it's actually very, very good. Considering that if you now go to 16th century or late 15th century, where Columbus is he's trying to persuade the Spanish royalty to fund his expedition to go to China using the western route, he is using size of Earth which is more like 25,000 kilometers. And that's because if he used 40,000, he could never get to China from Spain because he would run out of food and water. But he's not lying, because he actually does truly believe this Earth is much, much smaller, because basically the measurement of Eratosthenes was forgotten by then. And Ptolemy, who was famous in astronomy, also in geography, his values replaced the values that Eratosthenes has used. But in some ways, we can think about it that way. If Columbus knew this number, he would never even try to take the western route to China, because he would realize that it wasn't doable. And so that I always find it quite interesting. Okay, so anyway, this method has been refined. We can measure the size of Earth, of course, to extreme precision now using satellites. I mean, you put the satellite in orbit, you can actually measure the size of the Earth very well. So now we have measured size of the Earth. We can use the Earth as our base, and then we can measure distances to objects in the solar system. The good news about the solar system is that all the objects in the solar system obey the Kepler's third law. So if I measure the period of revolution of an object around the sun, then using the Kepler's third law, I can also measure the distance of the object relative to the distance of the Earth from the sun. So if I measure precisely a distance of one object in the solar system in centimeters, miles, inches, whatever unit I use, then all the other distances are related by the Kepler's third law. So I only have to measure, let's say, distance of the Mars. Problem with that is the Mars is actually kind of bright. When I try to measure angle of the Mars seen from different places on Earth versus stars, the stars are much dimmer, so that's actually hard measurement. You can get the measurement, but it's not very good. An idea was proposed by English astronomer, I think it was Edmund Halley, that you can actually, instead of measuring angles very precisely, you can use the transit of Venus across as seen from Earth across the sun, and when you time the transit of Venus from different places on Earth, it will take a different amount